All right, so yes, I wanted to credit the students who've helped, or in some cases done the real work. We have Julie Elliott, Yuning Fu, and Ronnie Graffenton. They're all here and looking for postdocs or permanent jobs. Tim Jensen is an exchange student, and Chris Larson. So old tectonic geodesy was all about velocity fields. We did our GPS campaigns or whatever. We processed the data, got velocities, and then we started trying to interpret them. But we're taking everything as sort of linear in time in most cases. New tectonic geodesy is about time series. This is from a proposal that I think NSF really ought to fund. But it shows transient events in Cook Inlet of Alaska. They're detrended about this time, and clearly you can see these big kinks. But again, we're looking at transients in time series, and we've gone from looking at long-term averages to short-term things, and we have to grapple with everything that's in the time series. We can't just average it out. And some of those things are not tectonic. So even if we're interested in tectonics, we have to understand the non-tectonic things. And the bottom line is motion is not linear in time. These are vertical time series. They show seasonal variations, plus some other things. And although the amplitudes here are large, this is typical. Vertical motions are never linear in time. It's always up and down. So the main causes of this, first of all, I think, are actually loading-related deformation. And this is deformation of the Earth because the Earth deforms due to forces by surface loads. There are some other effects and also systematic errors that can produce apparent such things. Now, the most notable, or most famous anyway, loading deformation is glacial isostatic adjustment. This is in the case of Fennoscandia after the last glacial maximum. This is data and model. But again, this is a long-term effect of changing loads. In Southeast Alaska, we see tremendous uplift in excess of 30 millimeters per year. This is due to unloading over the last 200 years, including what's going on at the present. So what we can look at this with these rapid vertical rates, we also get significant horizontals. The vectors here show horizontals. The largest horizontals are about 6 to 7 millimeters per year. That by itself has a huge impact on what you interpret in terms of tectonics because it's a big signal compared to many faults. I'd like to focus now on shorter timescales like these annual variations. The dominant control for seasonal and annual periods is hydrology. It's moving water around. And because of the timescale, elastic loading theory can be used. It's a purely elastic problem. Steckler et al. Looked at this for Bangladesh, where river loading is the issue. When the rivers are high, sort of in the middle of the year, the GPS stations are low. And they were able to model, using the river height data, model these time variations in GPS. Now, we can do GRACE. With GRACE data, we can do this anywhere in the world. GRACE gives us mass transport. Measures the time-dependent gravity field, and seasonal changes in both GPS and GRACE are due to seasonal mass redistribution. That's not true for the long-term trends, but it is true for the seasonal. Here are examples of the seasonal. These are the amplitudes of annual signals. The reds are the hot spots. And we can use this with GRACE solutions and spherical harmonics, as Yuning described earlier, to predict displacements. So these are comparing detrended GPS time series with detrended GRACE predictions for the seasonal variations. The blue are the GRACE. These little purple curve is a seasonal average model. The red are GPS, and the green is the GPS seasonal average model. You can see they track very well. This is from Alaska. There's also interannual variations. You can see this is lower than preceding years, and this is lower than preceding years. And it's true in both the GPS and the GRACE. So this is kind of a Kobayashi-Maru scenario here. I needed just a few extra seconds. But anyway, the key thing is that there's, you can see both the seasonal and the interannual variations quite clearly in the GPS and the GRACE, and they're quite consistent. So if you subtract the GRACE predictions, you can make a load-free time series. This is the raw, this is the load-free. Much more linear. You get up to, in some cases, a factor of 2 improvement in the sort of the scatter, but you can still see some little variations in there. Now, there's some subtler things. When we use, the ITRF has no seasonal variations. It's piecewise linear. And that's actually wrong. These seasonal variations are real and physical. So when we align things with ITRF, we can actually create some fictitious position variations by ignoring those. So what should we do? We need to actually include seasonal deformation in the ITRF. And if we want to look at tectonic trends and variations, we might want to look at these load-free time series, but that has to be done consistently with what we do for the ITRF, for the reference frame. There are some things on the to-do list, really getting robust error bars everywhere. figuring out what's the best way to express the seasonal. We were just using annual and semi-annual. And removing things like interannual variations and so on are a big deal. Thanks.